Welcome back, everybody. So this is where we stopped last time. We sort of introduced this big theta notation. We didn't go over it. We just introduced that we can do this. Okay. So we're gonna go in detail on these notations. There are 5 of them. So we're gonna go over all of them. Okay. So let's start. All right, so we're going to talk about time complexity. So if we take an example, so we're going to analyze this 2n to the power 2 versus a constant time n. Okay, but I have plotted a bunch of growth functions over here. Okay, from n factorial, which has the largest growth, to log n, which has the smallest growth. Okay, and then over here in this graph I actually focus the I enlarge the focus to this portion. Okay, all right, so when c equals 10, okay, this guy equals 10 and 2n 2, so basically 2n to the power 2 crosses cn at n equals 5, and you can see it over here. Let's see, right here, okay, at 50, right here. Okay, so when c equals 20, okay, so which is this graph, okay, this one, this graph, okay, so earlier it was this one, okay, c equals 10, and now it's c equals 20, so this is a linear graph. Okay, so 2n to the 2 crosses at n equals 10. Okay, so if I go here, right here, it crosses. Okay, okay, so this is the blue graph is 2n to the power 2. Okay, so as we can see that as c goes up, the crossing cn with 2n to the power 2 moves to right. Okay, but we can guarantee that it still crosses this this function 2n to the power 2 for all c. It's a matter of when at which point of n it crosses. Okay, but every time it actually crosses, so it's a matter of where in the line of n it happens. Okay, so for all c, all positive c, okay, it crosses somewhere. Okay, so then what's important is, right, what kind of a function of n is it? Okay, so basically it's not basically what kind of function n it is the most important. Okay, so it's not where it is crosses or anything. Okay, okay. Okay, so let's talk about asymptotic analysis of algorithm. Okay, so when we compare growth functions or algorithms, okay, we focus on input size, not coefficient. Okay, so we focus on input size n, not the coefficient of the cost function. Okay, so that means basically main focus must be the growth rate, which means basically what kind of a function the time cost function is. Okay, Tn is. So basically the kind of the function Tn basically governs the growth rate, not the specific constant inside of it. Okay, so we call this asymptotic analysis of algorithms. Okay? So there's a specific name for that, called asymptotic analysis of algorithm. So basically, it's the study of algorithm as the input size grows or reaches its limit. Okay, so it's a study of algorithm as the input size grows or reaches its limit. So it's actually kind of definition. If you should be able to convey similar kind of idea when this question being asked in an interview. Okay. All right. So let's talk about big O notation. Okay. So basically, so if we have a function, this is our time cost function Tn. Okay, and there exists actually a function Fn, which basically after this point always above Tn. Okay, so we call this kind of a function an upper bound. Okay, so upper bound basically upper or highest growth rate an algorithm can have. Okay, so upper or highest growth rate an algorithm can have. Okay, so if we take Tn, okay, be the true running time or the cost function, time cost, and Fn and any arbitrary function. Okay, and there's this situation in which for all n, after n equals n naught, and here it's actually 102. Okay, Tn is bounded up by Cfn, and we can see that, right? So Cfn always on top above the function Tn. So we say Tn is bounded up by Cfn. Okay. So then we can now define big O notation. So big O notation is Tn is in set O Fn if positive constant C and n naught exist in such that this condition true for all n greater than n naught. Okay, so this is a definition of the notation, big O notation. Okay, we say Tn is in. It's notice it's in is really important, and this set is really important. Okay, because there's a set of such functions, like this constant can be anything, right? So that means there's a set of such functions that obey this rule. So we say it's a set. Tn is in set big O of Fn if positive constant C and n naught exist such that Tn is always in between 0 and Cfn. Okay, all right. So so that's the condition, the relation. Okay, and for all n greater than n naught, and then before n naught it could be down as well. That's fine. Okay, and then we actually have actual situation that has this relation. For example, if you take the quicksort runs better than selection sort or insertion sort, but for small n's like 20, 30 like values, insertion sort runs faster than quicksort. Okay, so there are real examples. All right, so it's really important that we have this in. Whenever you describe this, you should have this is in, not just is. Means there's a set of such functions. Okay, all right, let's talk about big omega notation. So in this situation right here, this is my growth function of the algorithm Tn, and in this function basically this function always after this point always underneath Tn, Cfn. Okay, this is this function. Okay, so we call that a lower bound. Okay, basically we say Tn can go below the Cfn after this point. Okay, so that's what we are choosing. So let Tn be true running time and then Fn is some arbitrary function. Okay, so then for all n, in here it's 131 in node, Tn is bounded below by Cfn. Okay, basically it's saying that Tn can go below this Cfn. Okay, bounded below by Cfn. Okay, so that's the lower bound. Okay, so it's basically the definition is lower or smallest growth rate the algorithm can have. Okay. So then we can define the big omega notation. Okay, so we say Tn is in set big omega of Fn if positive constant C and n node, okay, exists such that this relation holds for all n values greater than n naught. Okay, so basically it's saying that Tn is always above Cfn. Okay, so there exists a function that way. Okay, so that's the big omega notation. We call it the lower bound. Okay, again here we have in, that means basically there's a set of such functions, and there could be some, one goes like this, one goes like this, right? So that can be a set of some such functions. Okay, all right, so let's talk about big theta notation. Okay, so if the bounds are same within the constant factor, so here for example in this function, again this is our cost function or growth function Tn, the and then we have the C2Fn. Notice this, it's the same function Fn over here, but the constant are different. Here it's C1 and here it's C2. But the important factor is this guy, the Tn, is always sandwich between C2Fn and C1Fn. Of course, after this point. Okay. So when we have that situation, we use big theta notation. Okay. So for all n here, after in this it's n equals 55, Tn is bounded between, we say Tn is bounded between C1Fn and C2Fn. Okay. Now we can define big theta notation. So now Tn is, notice the in part is gone because now it's more certain. Okay, so Tn is big theta of Fn if positive constant C1 and C2 and n node exists such that, okay, this relation holds for all n greater than or equals to n naught. Okay, so here's the relation. So Tn is sitting between C1Fn and C2Fn. Okay, and again now we drop in to indicate exactness. Okay, so Tn is big theta of Fn. Okay, all right, so there are lesser known two more notations. Okay, so we covered the three major notations already, but there's a small o notation. All right, so one one thing with big O notation is basically it may or may not be asymptotically tied. It may be tied, it may not be tied as well. Okay, so for example, if we take 2n to the power 2, it's in big O fn to the 2. Okay, and then basically it is tight, and if we take the same function, we can still say that it's in big O of n to the power 3, but it is not tight, right? Because see that the power here is now more than that. Okay, so this O notation, this big O of n to the power 3 is not as tight as this. Okay, so this is a tight bound because it's the same order. Okay, it's tight, we say it's tight, but this is not. Okay, so basically big O notation, we use small O notation we use basically for to indicate upper bound that is not asymptotically tight. Okay, so in that, if it is not asymptotically tight, we can use the small O notation. Okay, so we can now define small O notation. Okay, so small O of fn, basically T is in set small O of fn for any positive constant. Okay, so see that the difference between the wording, right? For any positive constant c, there exists a node such that this relation holds. Okay, okay. So for example, for any constant c, positive constant, this relation holds. Okay, so Tn is always less than Cfn. Notice the equality is gone. Okay, for all n greater than or equals n naught. Okay, so again, there's a set of such functions, so we say it's in. Okay, all right. So basically, big O means the bound hold for some C, but small O means the bound holds for all C's. Okay, all right. Again, that n node can be different, guys. Okay, so the place where it crosses. Okay, it's an example. 2n to the power 2 is in small o of n to the 3. Yeah, okay, is in small o of n to the 3, but 2n to the power 2 is not in small o of n to the 2. Okay, all right. So we cannot say 2 times n to the power 2 is in small o of n to the 2. We can say 2 times n to the 2 is in big O of n to the 2. Okay, and that's what we said earlier, right? Okay, right here, right? Small 2n to the power 2 is in big O of n to the 2. Okay, so the difference again, it works for any positive constant. Okay, and you can see that, right? So see this, the order is more than that one, so it's always on top. Okay, all right. So similarly to small O notation, there's a small omega notation. Okay, so and then basically again similar to big O notation, it works for the small omega notation works both asymptotically tight and not tight situations. All right, so again here 2n to the power 2 is in small omega, excuse me, big omega of n to the power 2, and that is tight. Okay, so 2n to the 2 is in omega n is not tight. Okay, so so then we can define a small omega notation. Okay, so it's a lower bound that is not asymptotically tight. Okay, so if the bound is not tight, then we can use small omega notation. Okay, then we can define small omega of fn So Tn is in set small omega of Fn for any positive constant C and N nodes, and if we can have this relation, then it's a small omega, it's in set small omega of Fn. Okay, so you can say that it's for any positive constant beyond N naught. Okay, so it's always on top of Cfn. And again, you can see that the equality is gone over here. Okay. All right. So again, there's a set of such functions, so we say in. Okay. All right. So big omega means the bound hold for some positive constant. Small omega means bound hold for all positive constant. Okay. All right. So 2 times 10 to the 2. So this is an example. 2 times 10 to the power 2 is in small omega n. Okay. But 2 times n to the power 2 is not in small omega of n to the 2. So we cannot say that. This hold only for some constant, not all constants. That's what we say it's over here, right? So we cannot say 2 times n to the power 2 is not, we cannot say 2 times n to the 2 is in small omega of n to the 2. Okay. We can say 2 times n to the 2 is in big omega of n to the 2. Okay. Right. So that's what we say earlier, right? Right here, right? 2 times n to the power 2 is in big omega of n to the 2. Okay. All right. So there are some set of rules that we need to go over. They are actually coming from, so this we are dealing right here is positive functions, right? So the time or space we measure is a positive function. So they, as even as functions, behave like real numbers, and then that's the reason that we have this set of rules coming. Okay, so the first one is transitivity. Okay, so we have, so if we take if Tn is big theta of Gn, and Gn is big theta of Hn, that basically imply Tn is big theta of Hn. Okay. All right. So and then we can go on the same similarly to other notations as well. So if Tn is in big O of Gn and Gn is in big O of Hn, that imply Tn is in big O of Hn. Okay, so and we can actually I'll try to graphically explain one of these examples. Okay, so oops. Okay, and same hold for big omega, same rule hold for small o, same rule hold for small omega. Okay, so that's the transitivity. So basically, in conclusion, we can say if a function Gn bounds Tn, then any bound of Gn also bounds Tn. So that's actually Hn, right? So any bound of Gn, which is Hn, bounds Tn. Okay. So what are the bounds? These are the 5 bounds. Okay. All right. So it's an example. Tn is in big O of n to the 2, and we know that n to the 2 is in big O of n to the 3, so that means basically Tn is also in big O of n to the 3. Okay, right? So here n to the 3 is like our Hn over here. Okay. All right. So let's go to the second rule. Okay. So if there's a constant factor, okay, and if k is greater than 0, then we can basically say Tn is in big omega of Gn. Okay. Sorry, big O of Gn. Okay. And it's valid for any notation. Okay. So we can simply ignore multiplicative constant. What I was saying is any notation, this could be big omega, this could be big O, this could be small o, this will be small omega, this could be big theta as well. Okay. You can ignore multiplicative constants. Right, so if, for example, if Tn is in big O of 10 times n log n, then we can say Tn is in big O of n log n. So you can simply ignore these constant factors. So we continue with rules. Okay. So if there are two cost functions T1n that is in big O of Gn, G1n, and T2n in big O of G2n, then the sum of the cost, the notation, the cost analysis between the sum of the function is in the maximum of the two G1n and G2n. Okay, which one is has the higher which one basically it's saying that which of the two has the highest bound. Okay, and that governs the final bound basically. Okay, so basically this is basically take the most significant growth function, most significant growth function govern the complexity. That's what it means. Okay. All right. So in sequential program, so that means we should only focus on the most expensive part of the code. Okay. So Tn, if we have like this, Tn is in big theta of n plus big theta of n to the 2, then we can ignore the smaller, less significant part and say that Tn is in big theta of n to the 2. Okay. So because this guy governs the overall growth of the function. Okay. So there's a code example. Okay. This is actually book has the same thing there. Okay. So we have this. This is a single for loop. Okay. So this is like big theta of n. Okay. So it grows linearly, right? Because it's a single for loop, and it's big theta of n. And we have a double for loop over here. Okay. And it's a nested for loop, and one inside the other, and then both runs up to n. Okay. So there are n to the 2 amount of iterations here. So this part runs big theta of n to the 2, and the total cost is basically the sum between these two. Okay, so that means we can take the total program that runs in basically big theta of n to the 2. Okay, we are continuing with rules. Okay. Excuse me. So if T1n is again big O of G1n and T2n is in big O of G2n, then the product is in big O of G1n times G2n. Okay, so the product of the cost function is in big O, the product of the two bounds. Okay. So that means basically nested loops shows this behavior. Okay, so we will see that in an example. So if we take an example, T1 is in big theta of n and T2 is in big theta of log n, then Tn, the overall growth cost over time complexity is equal the product between the two. You can say big theta of n log n. Okay. All right. So here's a code example. Okay. So outer for loop runs big theta of n. Okay. And then here in this inner for loop, okay, you can see that it's star equal. That means every time j gets double, okay, at each iteration. So so that means basically this part runs big theta of log n. Okay. So the overall for both for loops, it's the product of the cost functions. Basically, it's a big theta of n log n. Okay. All right. Continuing with rules of analysis. Okay. Reflexivity. Okay. So theta n is big theta of Tn. Okay. So if this is the case, okay. Sorry. If if we have a growth function, it's in itself of big theta of Tn. Okay. So that means basically if Tn is n to the 2, okay, so n to the 2 is also in big theta of n to the 2. Okay. The function itself in the same order. Okay. So same in the same growth category. Okay. So say it's valid for big O as well. The same rule valid for big O as well and big omega as well. Okay. So call this reflexivity. Okay. Notice it's the same function. Okay. And here as well. Okay. Function itself is in the same analysis. Okay. All right. Symmetry. Okay. So if Tn is in big theta of Fn, then basically Fn also is in big theta of Tn. Okay, so we can actually take a look at this. Okay, let me go to the Jamboard. So I'm gonna go to. I already set this up. Okay. Okay. All right. So this is what we have, right? So we say Tn is in big theta of Fn. Okay. So now we can draw similarly. We can draw. Similarly, we can draw Fn as well. So let's say Fn is like this. Okay. So this is Fn. That's Fn. Now we can find two more functions. Basically, that goes like right here. And sorry about that. Let me do that. Right here. And another function. So that means like this is C, let's say C4. Now this is Tn. Okay, and this is C3 Tn. Okay. Now this is the other way around, right? So now this guy is the focus, and we can write Fn is basically big O of is big O of big O of Tn. Okay, so it's the idea of okay, so that's the idea of symmetry. Okay, so let's go to the slideshow. Symmetry. Okay, and then this transpose symmetry. Okay, so if Tn is in big O of Gn, then basically Gn is big omega of Tn. Okay, so right, so if Tn is in big O of Gn, that holds only if Gn is in big omega of Tn. So let's prove this as well. Okay, so I'm gonna finish the slide and then we're gonna prove both of them. Okay, and the other way around, if Tn is in small of Gn, and that basically only happen if and only if Gn is in small omega of Tn. Okay, so let's talk about that as well in the Jamboard. Okay, so basically, so now this is, we can see that, right? So this is Tn and this is Cfn, and this is the situation that we have. We say Tn equals is in big O of Fn, right? And we can see that if we focus on this function, our Fn function, okay, and then that's actually lies on top, right? So okay, so basically we can say now Fn, right? Fn is above, right? So if we take like for some value of Fn, like this, that's Fn. Okay, okay, for Fn, right, we can write is in big omega of Tn. Okay, notice that, right? It's always Tn lies below of Fn. Okay, so that's what it means. Okay, so so if that is the case, so that's if this is the case, and then this hold true as well. So in other words, only if this is true and this is true, and then vice versa. Okay, okay, all right, and then okay, so let's go back to our lesson. So you're over here. Okay, all right, all right, so we are continuing classifying functions. So so now the question is, if we have two growth functions, then how do we classify the symptotic relation between the two? Okay, so let's talk about that. Okay, so for example, we have, okay, so we have Fn equals n to the 2 and Gn equals 2 n log n. Okay, so basically then we need to ask the question, is Fn is in this or this or big theta. Okay, so notice I picked small o and small omega notation. Okay, because that covers the overall picture. Okay, that's why. And then big theta. Okay, so the question is, how do we determine, okay, the relationship between Fn and Gn? Okay, so how do we say whether Fn is in small omega of Gn, or sorry, small o of Gn, or small omega of Gn, or big theta of Gn? How do we determine that? Okay, all right, so to do that, we're going to take this limit. Okay, so we know the functional form of both functions, exact forms. So we take this limit as n goes to infinity, Fn divided by Gn. Okay, and if that goes to 0, okay, then Fn is in small o of Gn. Okay, so basically this limit goes to 0 means after some point n naught, this guy is always bigger than this guy. So the ratio goes to 0 when n goes to infinity, right? So then basically this guy is the upper bound because this guy is larger, right? So it's a small o of Gn. Okay, right? Here's an example. Fn is 5n, Gn is 10 to the n, 10 times n to the 2 plus 50. So Fn less than Fn divided by Gn goes to 0. That means we can say Fn is in big O of Gn. So this is the way to determine easily the relationship between two functions, whether it's small o, small omega, or big theta. Okay, all right. So, and then this valid for big O as well. Many books, some books take the big theta, big O here. Okay, but some books takes small o because that covers the overall, like all the functions, right? So it's not tied for a given amount, given c value constant. So this is good for all such constant. That's why I picked this one. Okay, so how do we prove this, right? So I'm gonna quickly go to the Jamboard and then take a new one. See, all right. So we have phi n, right? So Fn equals phi n, and Gn equals I think it was, let me just take a look. Oops. So it's 10n to the 2 plus 50. Okay, so 10 times n to the power 2 plus 50. Okay, so we take the ratio. Okay, so Gn Fn divided by Gn, and then take the n limit. Okay, so we have this phi n. Okay, and you have done this in your calculus class. Okay, so how do we prove this? We take n out. Okay, so phi n, and we take n square out here. Okay, 10 plus 50 over n to the 2. Okay, so n cancels off, and when n goes to infinity, so this goes to 0, and this whole thing goes to 0 because there's one n over here, so everything goes to 0. Okay, so that means basically this guy, after some constant, this guy is always on top of this guy. So if you want to draw the graph, right, so this is going to be Gn, and this is going to be always Fn. Okay, and for all constants, that's why I picked the small o notation. Okay, so we say Fn is in small o, sorry, small o of Gn. Okay. All right. So let's go back to our lesson. Okay. Okay. So small o of Gn. That's an example that we did. So next one is again we covered that one. When it goes to 0, if it goes to infinity, then Fn is in small omega of Gn. Okay. All right. Here's an example. Fn is 10 to the n2. Gn is 10n plus 50. So Fn over Gn ratio goes to infinity because this function, okay, so this function, it always lies underneath of this function. Okay. Well, after some constant, obviously. Okay. So after some n naught value. Okay. So so the ratio goes to infinity. That is the case. So this guy is always underneath. So this guy is bounded um, bounded below by this one. Okay. So it's big omega, small omega of Ga. Okay. So I'm going to cover the next one as well. Then I'll show you how. Okay. So next one is how do we find out whether it's big-Theta notation. Okay. So here's an example. Okay. If the ratio goes to a positive constant, then Fn is in big-Theta of Gn. Okay. So here's an example. So Fn is 10 n to the 2. Notice the same order over here. Okay. So we are dealing with big-Theta notation here, right? So and then Gn is n to the 2 by 2 plus 5n. So we got the ratio, and it goes to 20 when n approaches infinity. So that means it's a big-Theta of Gn. Okay. So let's take a quick look at those two as well. Okay. So here it's we had 10 to the okay, so this slide 10 to the n2, 10 times n to the 2, and then 10n plus 50. Okay. So Fn equals 10 n to the 2, Gn equals 10n plus 50. Okay, so we take the ratio Fn over Gn as n goes to infinity. Okay, so how do you write this? We have 10 n to the 2 and we take n out. Okay, so 10 plus 50 over n. Now we apply the limit. This guy goes to 0 and one of the n cancels off. So when n goes to infinity, this whole thing goes to infinity. Okay, so then basically Gn, okay, right, always underneath Fn. Okay, so that means like this situation. Okay, or after some constant always, right? So this is Gn, this is Fn. So basically Fn is in big omega of Gn. Okay. All right. So let's go to the next one. Next example. We have this one. Okay, 10 into the 2, and then into the 2 by 2. Okay. All right. So Fn equals 10 times n to the 2, and then Gn equals n to the 2 by 2. Okay. And you can clearly see that, right? The ratio of the two function, 10 n to the 2 by n to the 2 by 2. So n to the 2 cancels out. It's 20. So this is that constant that we were talking about. See? So it's when n goes to infinity, right? So this is approaching 20, right? So that means Fn equals big theta. You can write it equals or is Fn, sorry, Ga, right? All right. So let's continue. All right, so far we talk about the time complexity. Let's talk about space complexity, okay? So remember guys, I took t as the symbol for our function because I wanted to sort of highlight the fact that we are dealing with something related to the efficiency of running time, okay, it's time t, right? So many books use fn and gn both in this situation that is more general, but I wanted to take time as the resource there, so I kept Tn as our focus or highlight. So now the highlight is space, so we can take it as S. Okay, so space complexity. So far we have been discussing time complexity. Now we're going to discuss space complexity. Okay, always we know that mostly, right? Not always, mostly time complexity is the priority. Okay. So if we take, what about the space then, right? Memory or storage as a resource. Okay. Same rules applies to time that we applied time analysis. Those same rules apply here as well. Okay. So the differences are basically, right? There are small differences to time analysis concentrate on the algorithm of the data structure. Okay. Space analysis focus the data structure itself. Okay. Makes sense, right? Because we deal with memory with the data structure, not the algorithm, right? So, and here are a few things. Do not count the input data structure into space complexity. Okay. So that's your input. That's you are working with. Okay. So if your algorithm work in place of the input of that input data structure, okay, then and then doesn't use a new data structure or new amount of space, then the space complexity Sn is a big theta of 1. We say this is constant time. Okay, constant time, big theta of 1. Okay, so for example, if we take linear search and the array we get, that is the input. Okay, so Sn is big theta of 1. Okay. Okay. We are talking about storage over here, guys, not the time. Okay. So we know that Tn is big theta of n, right? Okay. All right. Sometimes we need extra space to make data structure work. Okay. So if we take linked list, for example, we need additional storage to store those pointers that we are dealing with. Okay. So this additional storage is called overhead. So we're going to go over this topic in detail in our linear structures lesson. Okay. So there are these two things. We can sacrifice some of the space, right? We can spend more space to gain speed, or the other way around. Okay. And we call it space-time trade-off. Okay. So basically, There are two examples here. We can pre-store common steps in an algorithm in a, let's say for example, new array to save time. You know that array access is order 1, so if we pre-store, then we don't need to like use a loop or anything to access. We can directly access those values. Okay, so we can, that way we can pre-store common steps, and then to use it later, so that there we sacrifice some space to gain speed. Okay, on the other way, basically we can compress data to save space, but we know that data compression is an algorithm, so it takes time. Okay, all right, so spend time to compress data and to save space. Okay, and for example, this space complexity is more important when you actually want to program a chip. You know that in a CPU or in a chip, that's really small amount of memory, so that's the, so they are the highlight, or the most significant cost is actually space, could be space. So you want to save this space by compressing the data, so you spend more time there. Okay, compressing. How about when we involve the disk? Okay, so this happens, by the way, whenever the operating system a computer reach to close, getting close to the total uh, uh, RAM memory and total memory the system have, it's going to start using the a specific place in the hard drive as the storage of memory. When that happens, basically, um, we know that the system gonna get slowed down significantly. Okay, so we call it basically disk-based space-time trade-off. Okay, so here the smaller the reliance of disk is the better. So if we the less we depend on the disk, the better. Okay, and then the reason is obvious, because the seek time for a hard disk is like 1,000-fold slower than access to memory, even more than that. Okay, so even for the solid state disk these days, which is actually faster than disk based hard disk, even with that it is actually slower. Okay, so seek time of the hard disk is really slower, so it takes time. Okay, disk read is very slow. All right, so we in this in the previous lesson you saw that, okay, so why we need algorithms, and then right, and then I worked on an example as well. Having faster CPUs doesn't necessarily means improving a whole lot of speed. Okay, but why we still need fast computers? I mean, we know that Intel is a it's a big company and doing really successful, successfully growing, right? And then their goal is to basically improve the speed, the CPU speed, right? So the reason is this, right? So algorithm cannot address every part of the problem, right? So there's a limit that we can apply an algorithm, and it doesn't apply to all situations. Sometimes there's no algorithmic solution. And that could be that as well. And then we call it NP completeness. Okay, so we may be able to discuss this that a little bit. Okay, all right. And then also our algorithm solve only specific problem, but computers solve maybe 1,000 problems at a time. Right, computers do multitask. So that means, like for example, I'm presenting a Google slide, so that Google slide runs here, but I also use Qt underneath. So the both programs runs, right? So in order to facilitate multitasking, it's good to have faster and then CPU with many cores, right? So multi-core CPUs. So that's one. So then basically it's better to have this multi-core or increased intrinsic speed CPUs. Okay. All right, guys. So let's talk about few common misconceptions. Okay. All right. So upper and lower bound. So these are common misunderstanding that we may post in regards to analysis of algorithms. Okay. One is upper and lower bounds are different always. Okay. Okay. So basically, if the cost function is well known, all right, then the upper and lower bounds are same. Okay. So we say the analysis is complete, and we use the big-Theta notation for that. Okay. So if the cost function is well known, and that's the most important thing here. If that is well known, like for example, we were talking about like 2 times n to the power 2. That's a well known one. Okay. Then the upper and lower bounds are same. Okay. And that's basically we report it as big-Theta of fn. Okay. So it's not different always. Okay. So the next one is upper bound is worst case and lower bound is best case for a given value of n. Okay. So that is not the case. Okay. What what bounded is the growth rate, not the actual cost. Okay. So not the actual cost. Actual cost is for a given value of n. Okay. Okay. So growth, what we call the growth rate is the change in cost as change in input size n. Okay. For a given n, notice the difference, guys. Okay. Change in n and given n. So given n means the data, the input is given. So we know what is n. It's a specific. Okay. And then for the growth rate, we study the cost as a function of n. Okay. So then you cannot talk about growth rate for a given input. So that's what this means. Okay. Okay. So upper bound is not worst case, and lower bound is not best case always. Okay. So basically there are two things here, right? Can talk about growth rate for a given input. That's what it means. Okay. All right. So next one. All right. So these are misconceptions. Then the down below I explain actual the truth. Okay. So best case occurs when n smallest, or worst case occurs when n largest, and that is not the case, right? Okay. For any possible size of input, either case is possible. I mean that's for example, if you take a linear search in an array, right? So the array is given. If we are looking for is at the first element, that's the best case. If we are looking, the search key is located at the end of the array, that's the worst case. So either is possible. Okay. So all right. So locating search key at the end of the end is the worst case for linear search for both arrays of size 3 and million. Okay. So that means n is smallest is base. That's no such thing. Okay. Right here, right? Okay. Locating the search key at the end of the array is the worst case for both size 3 and million size array. All right, so there's another misconception. Always a single statement is a small operation. No. Okay. not always, right? For example, function call, in a function call, it depends on the function body. Okay, if the function body is just have only single one operation, then we can call it as okay, that's a small operation. But if the function body has multiple amount of simple operation, then we cannot say it's a simple operation. But we know that the function call is a single statement, right? So um, don't just because there is a single line of code doesn't mean it's a small operation. Okay. All right. The other one, big O, big omega, small o, small omega, and big theta are functions themselves? No. Okay. They're just notation. They are notational definition um, only. They are not growth rates. Growth rate is just a function. Like for example, 2 times 10 to the power 2 is a growth rate. Okay. All right. All right, guys. So this is the proof of the series sum. You can take a look at this. I already posted this in the lecture 1. Okay. All right. That will be it, guys. So I'm going to post a third lecture, which is on object-oriented programming and also the templates. And I'll show you guys how to write our own templates, which is really important going forward into our next few lessons.